Today we'll speak about boundary layers. Let's say we have a solid boundary. We'll call it to be the x-axis. Here we have the y-axis. Fluid is coming from the left with a constant velocity u. At a place that is very near the boundary, we would expect the velocity there to be 0 because of the no-slip condition. But what will the velocity be like at a place that is very far away from the x-axis? It will be nearly u, because I'm very far away from the solid boundary, right? So we can define a layer which we call the boundary layer. We assume that the boundary only has some effect on the fluids in the boundary layer, but not those beyond the boundary layer. The fluids there, we assume they are not affected by the boundary. Well, we know in real life this is not exactly the case, right? Only when we are infinitely away from the boundary will we get absolutely 0 effect from the boundary. But for us engineers, a certain degree of approximation is acceptable. So how good, how close to not having any effect, which is the velocity equals to this u, which we call it to be the mainstream velocity. What is the degree that we can accept? Usually it's 99%. So we can define the upper surface of the boundary layer to be the place where the fluids have achieved 99% of the mainstream velocity. What do I mean by that? Let's take a cross section here. At y equals to 0, that is when we are on the x-axis, when we are near the boundary, right? Our velocity will be 0 because of the no-slip condition. Well, I'm not talking about the velocity on the x direction, which we denote by lowercase u. Okay, we do not consider the vertical velocity component v here. I'm talking about the u here. So here the velocity will be 0, right? As I increase my y value, as I go up, what will happen? I'm farther and farther away from the boundary, right? Which means I should be less and less affected by it. So I should be less restricted by it, which means my velocity will be bigger and bigger. So right here, I find that I have reached 99% of the mainstream velocity. So here, I say that 99% is nearly 1. I can live with that. So bye-bye, boundary, I'm out of your control. So this is the meaning of the 99% u. Okay, so here we have the boundary layer. And for every x coordinate, the distance between y equals to 0 from our boundary to the upper surface where we reach the 99% of u line, we call this distance to be delta, which is the thickness of the boundary layer. Obviously, delta is a function of x, right? From our boundary to the upper surface of the boundary layer, we have to experience a velocity change from here 0 to here 99% u, right? So when x is small, delta is small, this is the case. I have to increase my velocity from 0 to 99% of u. When x is bigger, delta is bigger, this is still the case. So we see what effect. Do you agree that at that when x equals to a smaller value, our velocity will change more sharply? What does it mean for the velocity to change more sharply? It means du dy is a bigger value, right? And we know du dy is related to what? It's directly related to the shear stress. So we would expect the shear stress at x equals to a smaller value will be big, right? When tau is big, it means the effect of viscosity is more notable, right? So it means our fluid behaves more laminarly. Well, maybe this is not so scientific a term, but you get the idea. Our fluids there will behave more nicely, right? But as x increases, the flow conditions will also experience a transition. If our plate is is long enough, then we would expect the flow conditions to change from laminar to turbulent. Let's say if our board is this long, maybe we can see the transition in the flow conditions. Here we see the flow is laminar, right? Maybe start on from some point. We would expect a transition period. Let's say here, this period is a transition period, and then we reach the turbulent region. So here we can call it the laminar region. Here the flow is laminar. Here the tau is still big enough. But here in the middle we would see the transition. Well, the transition is very hard to study, so I'll not talk much about it. And after that, from that point on, we have reached the turbulent zone. But if our plate has a certain value, then down here, the fluid that is very near our boundary, here, the tau will still be big. So here, we would expect to see a laminar bottom layer. If we draw the velocity profile, the velocity at the turbulent region may look like this. Here, I said here, in the laminar bottom layer, the tau is still notable, right? So here we would see a relatively large velocity gradient. But up here, in the turbulent region, the velocity change may be less. So we will see something like this.